planning ahead for each side to know what optimizations were happening in the other. And that's the real payoff here. And the key property to keep in mind is when we're reasoning through these diagrams, we're thinking about cases like this rule firing and this rule firing, where we're sending a message to somebody else out there who's listening on this channel, or we're expecting to receive a message from somebody else out there who's sending to this channel. We don't have to know the logic or the algorithm that the context uses to decide what it will send to us at each moment. The way this relation is defined, we are forced to anticipate all possible behaviors of the environment. And that's just what you want to get a good modular reasoning principle about libraries and what it means for them to be correct. Yeah?
So is this the consequence of those unit diagrams?
I suppose you could say so. I mean, basically, is your question something other than, does this work because you got the definition right? Yeah. I guess the answer is yes. Any other questions here? Yeah.
The L for the diagram to the left. So
yep.
The for L and the exists L, they're not the same L, right?
They have to be the same L.
They have to be.
We're saying if the implementation can take a step that makes a thing happen that the environment can see, the spec must also be able to take a step that makes the same thing happen. Because if it didn't, the environment could detect the difference.
Okay, then can I understand R to be an abstract interpretation of P1 and P2?
Yeah. At least it's definitely an abstraction. It might not quite match the formal definition of an abstract interpretation, but intuitively that's a good way to think of it. Yeah.
Is there some underlying sequential execution model that the processes can take steps on, or is this they can only send, receive, and duplicate?
As we can see here, the only steps, when we get down to the sort of the leaves of a tree of rule applications, the only steps that don't involve message passing are duplicating or spawning off another copy of a duplicated process. So there's not much of interest here from a purely sequential perspective without message passing. Any other questions? Yeah.
I am somehow missing a sequential duplication. Is that something you can model with this duplication with parallelism?
Sequential duplication. What do you mean by that?
Something where you would have infinity of dots.
An infinity of dots? Infinity of what kind of operation?
The dot.
The dot. Oh, done? You mean an infinity of dones?
Like recursively define a process prefixing, so it can take unboundedly many steps forward without duplication.
You mean like some kind of recursive definition mechanism or a loop? Purposely is not included here. We use duplication to get that kind of feature in practice. And I think I'll show some examples that demonstrate how we get loop-style functionality with duplication.
Okay. Let's see what I read.
Okay. Any other questions? I think I'm about ready to bring up some Coq code. Yes?
Isn't that relation that P1 is less or equal than P2 is exactly that P2 simulates P1?
Yeah, so we call this a simulation relation. We often find the words refinement and simulation used interchangeably for this sort of thing in the literature. Did I see another hand in the back? Yeah.
So is the first relation is bisimulation then?
This is not a bisimulation, it is just a simulation. With bisimulation, you're effectively saying a run of either side can be matched by the other. With this version, which is just simulation, I'm saying a run of this side can be matched by this side, but I'm not making the reverse of that claim.
There's no reverse.
People do study bisimulation like that in the process calculus setting. I'm just choosing not to do that here. Yeah?
So in the hide rule, if the next action is a communication on channel C, does that mean that the process is stuck?
If you have a process P whose only enabled step is a communication on channel C, then no step is possible for the hidden system.
Okay, so how can you say that it can communicate internally on that? Oh, okay, because any communication has been hidden. Okay.
Right, for an internal communication, we get this empty label, which does not run afoul of this restriction.
Ah, okay. Thanks.
Yeah.
infinite application of the duplication rule is fine in the implementation side, right? You don't have any condition regarding stuttering in the triangle diagram.
Let's see. Just digesting the question. You can handle one of these steps in the implementation with either of these two cases, because here the label is allowed to be an empty label. Any other questions? All right, so again, I kind of feel like saying if you take one thing away from my lectures, this is a big idea to take away. It's surprisingly infrequently found in semantics classes, but it's a really powerful principle for modular proofs of interacting systems.
Semantics classes on this side of the Atlantic.
Okay, could be true. I haven't taken an exhaustive survey. So let me bring up the Coq version of this and wrestle with the screen here. So what do I do? Display on projector. Let's see. Okay. So, oh, I'll change the lighting again, yeah. So I think it was it about here? Or is this the right setting? Okay. So this is just the Coq definition of that grammar of processes that I showed before. The only perhaps surprising part is that the body of a receive command, which recall I wrote before as having a bound variable x, well, I'm going to avoid thinking about variables explicitly and just say the body is a function over the value received from the channel to a new process. And I'm just forcing all messages and channels, for that matter, to be nats to keep this simple. So I define a type of labels as triples, optional triples of an action, which is an out or an in, and a channel and a value. And here are the rules, including the symmetric cases that I chose not to draw on the board to save some time. I'll just leave this up here for a moment in case anyone had any lingering doubts about the Blackboard version of the rules and wants to see how things are really working here. But I assure you it is essentially the same thing. All right, and then here's the definition of refinement. It's in two steps. First, P1 refines P2 if there exists an R, which is a good simulation, and it contains the two processes in question. Good simulation is such that if P1 and P2 are related, and P1 can take a step, then either it was a silent step, and the new P1 side process is related to the old process on the other side, or there exists a process that P2 can step to with the same label, and then both the new processes are related by R. And then I define a bunch of tactics here, which we'll use shortly. And I just want to go through some of the classic algebraic properties of this kind of relation. Yes?
Getting back to Eve's question, so you're dealing with commutativity by having these two-sided rules, but when in Milner's presentation, the quotienting is also by associativity, to be able to unnest things in a parallel composition. So how is that working here?
I think that all just works out with the rules for lifting a step over a parallel composition.
Ah, right. Thank you.
Yeah. So let's see. Classic algebraic properties. Turns out it's a reflexive relation, and I've defined a tactic where we prove a refinement by giving the relation capital R that demonstrates this particular case, and just equality specialized to the proc type is enough of a relation when I'm trying to prove reflexivity. In fact, it's very easy to match a run of a system with a run of itself. Use the same run and expect equality to hold at each step. And transitivity works by this notation here, destruct one as, is pulling apart each of these refined proofs and naming the relation that appears in each one. And then essentially I'm writing here the relational composition of those two, positing the existence of an intermediate term where x is related to the intermediate term, and then we can continue from there, get to y using the other relation. And that goes through with some tactics that were defined up there. Let me give now an example of, I think this will work up towards showing a duplicated server and how this gives us loop type functionality. Add3 is a program that receives on channel 0. When something appears there, we'll call it n, and then we'll add 3 to it and send it to channel 1 and then finish. A really thrilling cloud service that I'm sure you're all willing to shell out the big bucks for. And we can define its cousins add1 and add2. And then notice add1 receives on 0, sends to 2. Add2 receives on 2, sends to 1. What if I composed add1 and add2 together and marked channel 2 as purely an internal channel? This should really be observably indistinguishable from add3, though there's some extra steps there, they're hidden to the world. And the way I can express this, I need to give a simulation relation to justify this relationship. I think I can probably make all these fit on screen. And this relation is basically capturing all reachable states of the combined system where they're both somehow running next to each other and the spec is trying to keep up with the implementation. So for instance, the original composed program is related to the add3, the simple spec. And then, let's see, here's the implementation in one reachable state. Channel 2 is hidden, and we have received some value n, and we're now ready to send it on channel 2. And in parallel, there's an add2 waiting to get it. That's on the implementation side. On the spec side, we've received the value, and we're immediately ready to send the +3 version of it on channel 1. And then if this send gets to step, it'll turn into a done, and add2 evolves into sending n+1+2 on channel 1. And that was a step that has no effect in the spec side. It's just an internal implementation detail of the left-hand side. And finally, when we've run to completion, we have 2 little dones sitting around inside a hide channel barrier in the implementation, and we just have a done on the spec side. So I'm just defining a relation that basically, consider we're building a kind of product automaton of these two systems, and this relation is characterizing all the reachable states of that automaton. But crucially, it needs to be ready for any non-deterministic n that might be received over channel 0. And then it's not too much work to prove this one. I've just defined what a coincidence, the right tactic, so that it is they do the work for us. We just have to give the relation, and then we check all the cases, consider any states of this product automaton, and single steps we can take from them that had better take us back into the same relation that we defined here. All right, so yes?
How straightforward would it be to automate the product construction?
You could use something like a model checker to automate the construction of this relation, and I don't think that would be too hard to do, but I don't have that prepared in my Emacs buffer at the moment, so probably best not to try it. Too hard probably means a few hours. I mean, not too hard probably means a few hours, yeah. Yeah?
You expect that this would also cover the universal quantification?
You'd have to be clever about figuring that out somehow, but I assume there's some method that isn't too strenuous of doing that. For finite programs like this, it should be straightforward. All right, so here's the crucial theorem that I had up there in the upper right corner of the board, showing that you can take 2 refinement facts and then combine them with parallel composition. And the simulation relation we use there is just that we have parallel compositions on both sides, and then the different components are related by 2 relations that we pull out of the 2 refinement hypotheses. I think I'll go fairly quickly through this and just suggest poking around this code afterward if you'd like to see more of the fine details of this. So I'll just finish this tour through a few nice algebraic properties. You can add a hide channel on top of two processes related by refinement, and this maintains refinement. So let's see, what am I doing here? Very similar kind of example to what I did before. If I add 3 and then add 7, that should be the same as adding 10. So it's the same kind of thing with an intermediate channel that's being used here, where now channel 3 is the final outcome and channel 0 is the original input. And define another relation, take my word for it, it's a reasonable one. And then, now we get to do so-called point-free style proof, where we don't have to give any simulation relations. We'll just use algebraic properties to show that adding 1 then 2, and then adding 7 gives us add 10. Because recall, we already showed this add 1 then 2 is the same as adding 3, so we should be able to reuse that fact in a nice black box way. So the way I'll do that is I'll first choose transitivity. Now I can pick any old rule to use to show what hiding 1 in this parallel composition is the same as. Well, let's use refine's hide channel to sort of recurse underneath the hide channel and find a refinement for that thing. So we have a 1 then 2 and then an add 7. Well, let's use the parallel congruence fact so that I'll switch to showing something this is equivalent to or refines into and something that this refines. Well, I already proved a spec for add 1 then 2, so I'll just reuse my existing work. This add 7 happens to be fine as it is. So now I've replaced add 1 then 2 with add 3. So notice that's the one change from the original statement here. I turned add 1 then 2 into add 3. And now I can use the fact that I just proved about an add 3 and an add 7 being equivalent to an add 10. And internally there is a simulation relation behind this fact, but we didn't have to think about what it looks like we did in the cases that were proved more manually. We just get this nice algebraic reasoning that plugs together results. Any questions here?
Yes.
Yes.
It's a bit too magic, so can you show the definition of add 10 again? Or?
Definition of add 10, sure. Oops. Down at the bottom.
So here what you do is all your definitions, all your examples are communicating on very precise channels.
Yes.
But you could make these proofs perfectly...
I could quantify over the channels and require disjointness as needed and still prove all of this.
Great. Thank you.
Yep. Yes?
I might have missed this, but where are the definitions of the refines, high channel refines are?
They are among the ones that I scrolled past. For instance, refine's hide channel is this lemma that you can add a hide channel on both sides of a refinement fact. It's a whole bunch of different congruence lemmas for the most part. Hide channel, par are both congruence lemmas saying you can take refinement facts and add extra constructions in a way that lifts naturally in some sense. All right. One last set of examples here. I promised I'd show some loops in action to show how duplication gives us loop-style functionality. Turns out we can define a relation here. This one actually needs a lemma that we proved by induction. I won't dwell on that here, but in the end we can add a dupe on both sides of a known refinement fact, and it remains valid. That's a non-trivial result because, well, I have that P implements P prime. Now I'm effectively creating infinitely many copies of P, which might interact with each other, and interact with the environment and serve as go-betweens between the two modes. Every different copy might be assuming a different role somehow. And yet, with all those possibilities, we can still show that the duplicated version of P refines the duplicated version of P prime. And that all comes down to choosing the right simulation relation. And if you're curious about the details, you'll find it up here if you want to go through this code later. But for now, that's a good fact to have. Basically, all the constructions we've looked at are congruences with refinement, or maybe refinement is a congruence for them, I forget. So now I can take the theorem we proved before about add 1, then add 2, then add 7 being acting in the manner of add 10, and I can add a duplication on both sides. So now we have an infinite number of